We talked yesterday at the conclusion of our gathering about certain specifics of ligands, the transition metal chemist's name for Lewis bases. The material which interacts with the Lewis acid transition metal atom or ion to form a sigma coordinate covalent bond. Most ligands are monodentate. That means the ligand in question, regardless of the number of non-bonding pairs which it may contain in its Lewis structure, in its valence electron structure, the ligand can only make one sigma coordinate covalent bond to a particular metal atom or ion. We looked at some examples: chloride ion, water, ammonia. Reminded you that you cannot really talk about the strength of a Lewis base ligand unless at the same time you pay attention to the transition metal Lewis acid with which the ligand is expected to interact. Like silver ion with chloride ion. Far dominates the interaction of silver ion with ammonia or water. But cobalt-3, which we reflected on from the data of Werner, interacts more strongly with ammonia than it does with chloride ion or water. H+, on interaction with any Bronsted base, can be looked at as a coordination phenomenon, because H+ supplies an empty 1s orbital to make this bond formation interaction, and the Lewis base supplies the valence electron pair, which becomes a bonding electron pair on bonding with H+. Ammonia wins the battle for H+, relative to chloride ion, relative to water. We know this from previous chemistry. With that, let's put these two bases on the board. We know that this grabs H+ much more effectively than this. Now, write a Lewis picture for this. It's a simple Lewis picture. Do it now. Put it on your paper. Lewis picture for hydroxide ion. The purpose of this Lewis picture is to wrestle with the question, which of these treated as Lewis bases, not Bronsted bases, can be expected to interact more strongly with Mn+. As examples of Mn+, we'll write down aluminum +3, copper +2. I could pick other examples, but that'll suffice. For hydroxide ion, I trust you all wrote this. Nothing fancy or difficult about this. Again, if the battle is for H+, hydroxide ion wins hands down, because the effective negative charge density of hydroxide ion far exceeds the effective negative charge density of ammonia. And when you're battling for H+, effective negative charge density is all that matters. Keep in mind in chapter 23, when we wrestled with the assessment, the rationale of strengths of Bronsted acids, we did this always on the basis of effective negative charge density assessment for the conjugate base of the acid, in order to determine the strength of the conjugate base in question to grab H+. But when you're considering interactions with metal ions, this can be a very different game. Now, hydroxide ion battling with ammonia for aluminum ion. Now, you should know the answer to this from your work in 2046 laboratory. Assignment 4. You remember doing this? I mean, assignment 4 wasn't that long ago, was it? This has not now become ancient history, has it? What'd you find out? Hydroxide ion versus ammonia with aluminum ion or magnesium ion. Who wins the battle? Hydroxide ion or ammonia? Which of these interact much more strongly with aluminum ion or magnesium ion? You did the work. What the results of the work tell you? Who wins the battle? Nobody remembers? You did do this work, didn't you? Oh no. Hydroxide ion wins that battle. Did you find out that magnesium ion, aluminum ion are both much more readily precipitatable with hydroxide ion than with ammonia? And if you take ammonia and mix it up with ammonium ion, now you can't even get a reaction with magnesium ion. Remember that? Assignment 4, 46L. And don't forget, I'm still and always will be this dirty SOB who expects you to take what you've done in laboratory and put it to use from a knowledge gain standpoint. Now let's talk about copper ion. You did this in laboratory too, didn't you? You did this in assignment 6. Maybe you'll know more about assignment 6 since it's not so much a part of ancient history as assignment 4. Assuming that you did assignment 4 before assignment 6. Who won the battle for copper ion? Ammonia won the battle. What's going on here? Pay attention to the valence electron configuration for this, valence electron configs. This got any valence electrons? You remember our considerations, which are also part and parcel of chapter 23 on assessment of Bronsted-Lowry acid strength of hydrated metal ions? You did that one in discussion class. You were asked to recognize that if the hydrated metal ion is noble gas electron structure, then you can assess the strength of the hydrated noble gas structure metal ion on the basis of positive charge density. You don't have to pay attention to anything else. Which tells us immediately why hydrated aluminum ion is a much stronger acid than hydrated magnesium ion, for instance. Okay? How many valence electrons do these noble gas structure metal ions have? 18. Magnesium ion is atomic number 12. How the deuce could it have 18 valence electrons? Huh? How many valence electrons, aluminum ion, magnesium ion, how many do they have?
8. None.
None. The valence electrons all went away in deriving these ions from their parent metal atoms. None. So when hydroxide ion versus ammonia interact with aluminum ion, interact with magnesium ion. It's rather like interaction with H+. The difference in strength of this interaction is dependent upon effective negative charge density and the positivity of the ion. The ion with the greater positive charge density interacts more strongly with H+, interacts more strongly with hydroxide ion. And the hydrated ion behaves more strongly as a Bronsted acid. But you know, you just told me, when copper ion's in the game, this thing wins. Why? What's copper ion got regarding this question that these ions don't got? Valence electrons, specifically d electrons. How many valence d electrons does copper plus 2 have? 9 of them. Well, do you think the presence of valence d electrons on a transition metal ion might have something to do with the strength of the bond formation interaction of the transition metal ion with this species versus this species as a ligand? Do you realize that if hydroxide ion coordinates, that after coordination, you still have 1, 2 non-bonding pairs on the donor oxygen atom, don't you? But after ammonia coordinates, have you any residual non-bonding pairs on the donor nitrogen atom? No. What do you think, electronically speaking, is the nature of the interaction with residual non-bonding pair electron density and the valence d electrons that copper ion has? Does that lead to a favorable, does that favor the interaction? Residual non-bonding electron density of the donor atom with valence d electrons of copper ion. Once again, really, this is nothing but a Coulomb's law consideration, now applied to coordination chemistry. After ammonia coordinates, no more valence electron density on the donor atom to interact with valence d electrons on copper ion. But if hydroxide ion coordinates, you got 2 non-bonding pairs remaining on the donor atom. Do these non-bonding pairs interact favorably with the valence d electrons of copper ion or any transition metal ion which has got valence d electrons? Now, that detracts from the strength of the interaction. Interesting, isn't it? So once again, we're forced to recognize the significance and meaning of the statement that you cannot talk about the ability, the sigma bond forming ability of a ligand without paying attention to the metal ion with which you expect the ligand to interact. Can't do that. Now with Bronsted-Lowry acid-base chemistry, that's a straightforward consideration because the interactions are all focused on, do I make a strong bond with H+, yes or no? Here, you got a whole slew of different metal ions that these things can be imagined to interact with. And you have just been asked to consider the reason why, at least the reason that transition metal chemists offer, and I think it's a sound reason, why this thing beats this thing when it comes to interaction with transition metal ions which still have valence d electrons. That results in Coulombic repulsion between the d electrons, the valence d electrons of the coordinated metal ion, and the residual non-bonding electron density on the donor atom. That weakens the interaction. Does this argument tend to suggest to you why this thing behaving as a ligand is generally poor? This is an atom of appreciable electronegativity that retards its ability to share non-bonding electron density and make a sigma bond. Plus, after interaction, this thing has got 1, 2, 3, count them, residual non-bonding electron pairs. Now, based on size, we can expect a far greater negative charge concentration here compared to here because this is a much smaller atom, and that's true. But as a ligand, this is generally feeble. But if you ask this ligand to fight with this ligand or this ligand for this metal ion, now it's a different ball game. We talked about this, didn't we? Now this ligand wins. This ligand interacts more strongly with this than hydroxide ion or ammonia. In fact, we demonstrated that at the end of chapter 19 when we did some chemistry, which is chemistry that you also do in laboratory. In this case, again, assignment 6. Where by experiment you found out, if you did assignment 6 correctly in the laboratory, a chloride ion beats the pants off ammonia or hydroxide ion regarding bond formation strength of bond formation interaction with silver ion. And the question we asked about this yesterday was, are you going to attribute the stability of silver chloride to the strength of the sigma bond which forms when chloride ion interacts with silver ion? You better not. Because what we've just recognized is chloride ion makes pretty weak sigma bonds. You put H plus in here and forget this. This goes no place in water solution. Water molecule beats the hell out of this in water solution if the fight's for H plus. Well, water molecule has no chance against this if the fight's for this thing. Stability of this based on sigma bond strength? Forget it. Let's ask another question. Do you think silver chloride, and notice the similarity of the formula AgCl to NaCl, both binary metal-nonmetal compounds of elemental chlorine. Silver chloride, sodium chloride. Sodium chloride you know to be a crystalline substance, highly ionic in character, quite soluble in water, and if you make a melt of this, you'll find out it's a marvelous conductor. Because in melting, you've defeated the ion-ion interactions, which maintain the structural integrity of the crystal lattice, to the extent that the sodium ions and chloride ions can now flow past each other, or around each other. So you've got a good conductor. You think silver chloride is significantly ionic in character? I drew the formulas for silver ion and sodium ion purposely to remind you that this is a lot bigger ion. As an isolated ion, this is going to be a lot bigger than this. You think silver chloride is considerably ionic in character. If silver chloride was considerably ionic in character, what do you think you'd observe regarding its water solubility?
Soluble.
Be damn soluble. The ion-ion interaction strength is far greater between sodium ion and chloride ion than it is between silver ion and chloride ion, because for no other reason the positive charge density of this has got to exceed the positive charge density of this, because they're each +1 and this is a lot smaller. But yet we know this stuff isn't very soluble in water at all. Which suggests strongly that the silver chloride stuff isn't very ionic. What would you do to find out?
Melt it down.
Take the silver chloride sample of pure stuff, melt it, and then what?
Try to conduct.
See what kind of conductivity it exhibits. What kind of conductivity do you think molten silver chloride does exhibit? Poor. It's a lousy conductor, because as if by magic, When silver ion meets with chloride ion, making this very stable stuff, these things lose their ionic character. This stuff is molecular in character. It's covalent in character. Much more so than being ionic in character, which again is shown to us by the fact that molten this stuff is a lousy conductor. And we've argued that the stability of this certainly cannot be attributed to the strength of the sigma bond, which is formed when chloride ion interacts with silver ion. Well, then there must be another kind of bond which is stabilizing this stuff. We talked about this other kind of bond. Pi bond. Or pi bonds. And the model we've cast for pi bonding in a transition metal complex is that of role reversal, remember? Now the metal ion behaves as the Lewis base and supplies d electrons to make pi bonds. Metal ion has no choice if it's going to make pi bonds, and it, in so doing, function as a Lewis base because the metal ion hadn't got any valence p electrons, the transition metal ion. Okay. The silver ion got a rather significant complement of valence d electrons? Hell yes, 10 of them. They're all there. 4d electrons. The 4d sublevel is full. Well then, if silver ion, in bonding with chloride ion, if silver ion is going to behave as the Lewis base and make pi bonds as a consequence of using d electron density supplied by silver ion, then the chloride ion is supplying what to make this pi bond interaction? To pave the way for this pi bond interaction. What's chloride ion supplying? Empty valence orbitals capable of pi overlap interaction. What are these empty valence orbitals that chloride ion has?
P orbitals.
What are they? Empty valence orbitals that chloride ion has that can make pi bonds. What are they?
3D.
3D. How about this? Can this make pi bonds like chloride ion? Can you put any more electron density in the valence environment of fluoride ion? Why not? Don't tell me what it hasn't got. Tell me what it has got. Well, it's got noble gas structure, so does this. Fluoride ion has a full complement of valence electrons because fluoride ion has only valence 2s and 2p orbitals. Because fluoride ion is derived from fluorine, an atomic member of period 2. So once you look at fluoride ion, in terms of its Lewis structure, see 1, 2, 3, 4 non-bonding pairs. You can't put any more electron density into the valence environment of this thing. It's completely saturated. Chloride ion not. That's got valence d orbitals, not period 2 atoms. So if silver ion interacts with fluoride ion, you think you're going to get a material that's as stable as silver chloride? You think you get a material which has got a considerable degree of ionic character? Yeah. How about that? Interesting, isn't it? Now, on we go, peeking more at ligands. We talked about monodentate and polydentate ligands and reminded you that the most common polydentate ligand is bidentate ethylene diamine. So I showed you this model. I took away the hydrogen atoms from the skeletal carbon atoms. They're not necessary because they've got no effect on the chemistry we're of a mind to consider. And reminded you that along any single covalent bond with no multiple bond character at the bond site, you have free rotation. So if ethylene diamine in solution shows this shape, It can also show this shape by rotating along these carbon-carbon and carbon-nitrogen single bonds. And it can also rotate along the carbon-nitrogen single bonds in order to get these non-bonding pairs to aim at the same location in space. And that's when I showed you that if my head is a metal line, then I can wear my nice, beautiful Easter hat. Because now I'm chelated. I'm doubly coordinated by this ligand ethylene diamine. And I also ask you to count the number of atoms in this ring. 5, because that has a bearing on stability. Any of you look at bonus quiz 3 yet? Think number of atoms in a ring might have something to do with ring stability? Here's another common bidentate ligand. Abbreviational reference is OX, because this is oxalate ion. Condensed formula is this, C2O42-. But watch out, this formula can be seriously misleading. Here's the Lewis structure for oxalate ion. I should really write this like this. But still that does this injustice to its structure. Sometimes you're just up against it when you try to write the formula for a chemical species and in so doing convey structure. For oxalate ion, you got a problem. I mean, you might look and say, do I have oxygen-oxygen bonds? You don't. Now then, if this is swimming around in solution, then a metal ion could approach this from this side, this side, this side, this side, any which way. There's just particles floating around in solution. In order to recognize the bidentate character of oxalate ion, where do you think the metal ion should be when it contacts the oxalate ion? Should it approach the metal ion, pardon me, should the metal ion approach the oxalate ion on this side or this side? Does it matter? It matters. Notice that if the metal ion approaches this side and coordinates with non-bonding electron density from this oxygen and simultaneously this oxygen, I will have how many atoms in my ring? 1, 2, 3, 4, 5. But if this interaction takes place, how many atoms in my ring? 4. 4 is not very stable, but 5 is quite stable. That's why I asked you to look at the number of atoms when I put on my Easter hat. Count them up. We'll talk more about the 5 versus 4. Number of atoms in the ring. Another question. All right? From atom count, we recognize that for oxalate ion to do its bidentate thing, the metal ion needs to approach on a side-on fashion, not end-on. Okay? Question. What happens to resonance on coordination? Do you realize that oxalate ion by itself shows resonance? You know, I could just as soon rewrite this and show negative charge here, negative charge here, negative charge here and here, negative charge here and here. What happens to resonance when this thing coordinates? Still got resonance? Resonance goes away. What happens to the net positive charge density on the metal ion when this thing coordinates to it? What happens to the net positive charge density on the metal ion when this thing coordinates to it? What happens to the net negative charge density on this thing when this thing coordinates to this? Well, let's draw a picture. One of these non-bonding pairs has got to be used to make this coordinate covalent bond formation interaction. One from each of the oxygen atoms. All right? Now I'll calculate formal charge on these oxygens. Will they still be -1? What are the formal charges now? 0. What's now the charge on the metal ion? It's N plus plus -2. The -1 formal charge from this oxygen was transferred to the metal ion. The -1 formal charge on this oxygen was transferred to the metal ion. The formal charges can't evaporate. We didn't add electrons to this thing. I mean, if nothing else, I'm giving you, I hope, a greater perspective on what you can do with these Lewis pictures. You can do all kinds of stuff with these things. That's why they're so important to write correctly. And now we've answered the question. What happens to resonance? Still got resonance? No. Went away. Nitride ion. Let's apply what we, I hope, just achieved from this conversation. Nitride ion is a monodentate ligand. Nitride ion is a monodentate ligand, but it is capable of forming an isomeric behavioral interaction with transition metal ions that's referred to as linkage. More to the point, nitride ion. It's got non-bonding electron density on its central nitrogen atom, as well as abundance of non-bonding electron density on its peripheral oxygen atoms. And resonance. But this thing can coordinate through nitrogen or oxygen. That gives you this linkage term. It's different linkage. Has it linked to the metal ion through nitrogen, or is it linked through the metal ion through oxygen? Non-bonding electron density from nitrogen or oxygen. Okay? What do you think? You think this would more likely coordinate through nitrogen or oxygen? In coordinating with a transition metal ion. Remember what we said over here? What's your bet? Nitrogen. Because if you coordinate with oxygen, you still got residual non-bonding electron density. Another question. If this thing coordinates through oxygen, what happens to resonance? Goes away. Does resonance seem to contribute to valence electron density stabilization for the species which shows resonance? You're damn right. That's a destabilizing effect. Do I lose resonance if this thing coordinates through nitrogen? If this thing coordinates through nitrogen, do I wind up with an effect like that? No. One more. Thiocyanate ion. How many of you in finishing 46L did work in assignment 10? Well, if you did work in assignment 10, then you did some chemistry with this stuff. You found out that this stuff is a particularly strong ligand toward iron 3+. Do you think when SCN minus or NCS minus, because we've shown you the two acceptable Lewis structures for this anionic species, and its Lewis picture should show you this, like this, can make linkage isomers. This can interact as a coordinator with non-bonding electron density from nitrogen or instead from sulfur. If this thing interacts with iron plus 3, which of course you know it does if you did assignment 10 in the lab, you think the bond formation interaction with iron plus 3 is through sulfur or through nitrogen? That's right. Why? You know me. Why is the question you got to answer. Well, let's put silver ion in the game. If this thing coordinates with silver ion, you think the linkage is through nitrogen or sulfur? Just for some, well, you did this in 46 laboratory. Did you find silver ion to show particularly strong tendency to bond with sulfides? You find silver sulfide to be a damn stable stuff? Can you dissolve silver sulfide by treatment with ammonia? Not today, not tomorrow. You can't dissolve silver sulfide by treatment with hydronium ion, even though sulfide ion is a potent base. Stuff too stable. Well, that suggests that if this thing behaves as a ligand towards silver ion, we should expect the interaction to be with sulfur rather than nitrogen. That seem reasonable? What other property of this bond formation interaction would drive silver ion to interact with this thing through sulfur? What other feature of this bond formation interaction? Remember what we talked about over here? Pi bonding. I can't do that with this, but I can do it with this. How about that? Interesting, isn't it? Now, on we go. We'll talk about more of this as our conversation on transition metal chemistry proceeds. Nomenclature, section 24.4. I'm not going to stand here and provide a lecture on how to cast a name. There is no theory that I'm aware of that will allow you to understand why. My parents decided to name me James. Charles for middle name. Other than my dad's middle name was James, and my favorite uncle from my father's side of the family was Uncle Charlie. You think I'm going to give you rules like that to learn? Pay attention to it. Section 24.5. Take a look at the table that you see at the bottom of page 24.6. The information which we will now consider will tell us about, or help us learn about, interpreting data to write formulas for transition metal complexes. And will also remind us about the strength of the coordinate covalent bond interaction. I've written for you the 4 formulas as they appear in this table. 1, 2, 3, 4. And then I've added a formula over there. We'll talk about that after we talk about these. Now, going along with this analysis, I want you now to start to develop the ability to draw pictures of coordination complexes. Pictures which will show the structure and shape of these species. And the most common structure and shape is octahedral. So here is a look-see of what's in the notes about how I want you to draw pictures for octahedral complexes. here's an octahedron. You've seen this before, I'm sure. Octa, 8, because this thing has got 1, 2, 3, 4, 5, 6, 7, 8 faces, each of which is a perfect equilateral triangle if these apex positions are all the same distance from the center of the octahedron, and these apex positions are taken by identical atoms. Okay? And this is a perfect octahedron. Octa 8, hedron face. But a ball and stick model is more convenient for us, because the ball and stick model shows us the atoms, including the central atom, and shows us bond angles, at least much more sharply and clearly than the solid state model does. Again, this is really a simple geometry. For a 6 peripheral atom species, this is a pretty simple geometry. You only got 2 bond angles of consequence for a perfect octahedron. 90, 180, we talked about that previously. And now we can show you how this chalkboard sketch relates to what I show you with the ball and stick model. Top atom here will go here. Bottom atom here will go here. And these 1, 2, 3, 4 atoms, which will be one at each corner of this canted square. Look at the red, the green, and the black. When I hold the red, green, and black, you see this is a square? Okay? So you got to understand that this square, when it's canted, is a pictorial representation of a square which is not in the plane of the drawing surface. This square is perpendicular to this drawing surface. These 2 atoms are closer to you and out in front of the drawing surface, and these 2 atoms are behind the drawing surface. In this case, closer to me and further away from you. To play this game, I offer a suggestion. I think you can all afford a piece of paper. Take a piece of paper, fold it or cut it into the shape of a square. And if you want, take a stick or a long pencil and push it through the center of that piece of paper. Because now you have a very poor but effective simulation of an octahedral species. Right? One atom up top, one atom down there where I'm holding this thing. And then if you want, you can take this square and you could label these things. Ammonia, chloride ion, whatever you want to put there. And then you can see what happens to the spatial positions of these atoms, which are part and parcel of this octahedral material, when this thing is floating around in solution, doing all these things. Because a lot of what we're going to now talk about will involve your ability to recognize what happens to the spatial positions of these peripheral atoms of this octahedral species, or whatever geometry we choose to talk about, when this thing is being blown around by the wind or floating around in solution. If we want to rotate this thing 90 degrees, you can take your piece of paper. Oh, you can do anything you want with it. I think you can afford this. If not, I'll give you a piece of paper. If you want a pencil, that's $1. Got to get some beer money, you know. Yeah, I think $2. All right. Now, look at the data. Specifically, moles of ions per mole of compound, moles of precipitatable chloride ion per mole of compound. These data mean respectively. If I take a mole of this and put it in solution and observe conductivity, I will find out that per mole of this compound I got 5 moles of ions swimming around. And per mole of this compound I have 4 moles of precipitatable chloride ion. I just dissolve a mole of this in solution and treat it with an excess of silver nitrate solution, and I precipitate a bunch of silver chloride. After I weigh the silver chloride and figure out how many moles I got, I get 4. For this stuff, 4 moles of ions. I say that's interesting because each of these things have got 4 moles of chloride ions as part of the composition. And for this thing, even though again I got 4 moles of chloride ions, I can't get 4 moles of silver chloride to form. I get only 3 moles. For this thing, 3 moles of ions and 2 moles of precipitated silver chloride. And for this thing down at the bottom, I get 2 moles of ions per mole of compound and 0 moles of precipitated chloride ion. And since I added this formula over here, I'm going to go over here and extend the table. Let's get this stuff out of the way. Let me ask you, what do you think I'm going to write in here for moles of ions per moles of compound for this thing? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 47,000. What do you think I'm going to write? Anybody wish to venture a guess? A yop? How about moles of precipitatable chloride ion? Nobody wants to take a shot at this, so we'll put that one back on hold. And we'll go over here. Now, in our conversation about Werner's chemistry, what did we find out about ammonia compared to chloride ion regarding liganding ability? In this case, toward platinum in the +4 oxidation state. Do you realize that the ammonia molecules are all 0 charge-wise, and these are all 4 -1 oxidation state chlorine atoms, commonly called chloride ions? Which by default means if this thing is a compound, that means it's neutral. This has got to be platinum in the +4 oxidation state. Every one of these materials for which I've written the formulas have platinum in the +4 oxidation state. Oxidation state analysis will show you that. All right? Now, I'll make another statement to you. Take it as a given. Transition metal chemists have found that platinum in the +4 oxidation state forms octahedral complexes. That's it. That's all it does. And ammonia molecules and chloride ions are each monodentate ligands. So what this is about, at least in addition to what we've already noted, is which of these Lewis base species, ammonia molecules, chloride ions, are to be found in the first coordination sphere. Based on the data, can we decide which species are coordinated and therefore in the first coordination sphere? Because they're chemically attached to platinum. And since platinum is a transition metal, we're looking at a species with residual valence d electron density, aren't we? Which, if nothing else, is suggesting to us why we can well expect ammonia to be a stronger ligand toward platinum-4 than chloride ion, which is indeed true. All right? If these platinum complexes are all octahedral, that means we've got 6 sigma bonds in that first coordination sphere, and these are all monodentate ligands, which means I got to have 6 ligands in that first coordination sphere. Well, if I can dissolve a mole of this and find that I have 5 moles of iron swimming around and 4 moles of precipitatable chloride ion, then it shouldn't be hard to realize that for material number 1, all the ammonia molecules are coordinated, and there's the structure of the species. Charge because this is an ion. What's the charge? +4. So, you've got 4 chloride ions ionically bound to this stuff in the solid state, but when you dissolve it, the chloride ions swim around their merry way, and you put in the silver ion says, aha, chloride ion, bleep, silver chloride, boom. Now, another part of this exercise is to use it to develop an ability to write formulas correctly for complexes, coordination complexes. Well, the rule of the road is simple. After you've determined the composition of the complex, you enclose such in brackets. So this is hexamine platinum 4 chloride. Hex for 6. An ammonia molecule as a ligand is called amine. A-M-M-I-N-E. You'll see that in the nomenclature stuff. Hexamine platinum 4 chloride. Now let's look at this one. Even though all the ammonia molecules are in the first coordination sphere, we cannot construct an octahedral coordination environment from the ammonia molecules alone because we only got 5 of them. So the difference between 2 and 1 is that one of these positions in the first coordination sphere, which is octahedral, is occupied by a chloride ion. Where do you want it to go? Does it make any difference? Now, I don't want to tear this apart. Imagine these at present. These are all ammonias. Okay? Chloride ion's coming in here. Where do you want the chloride ion to go? On top? Where do you want to go now? On top. Where do you want to go now? Always on top. Well, hell, if chloride ion's over here, runs over here, the chloride ion's going to go over here. Doesn't make any difference. These geometric positions are these octahedral positions are geometrically identical. They're equivalent. Doesn't make any difference. There's our octahedron. Who cares? Okay? Now, I'm going to put the chloride ion over there. And recognize that the charge of the complex has now been reduced to 3 plus from 4 plus. And now there's 3 moles of chloride ions ionically bound in the solid state. Do you see how these data correspond to this stuff? See how the formula's changed? Now in this first coordination sphere, and part of the complex, I have a chloride ion. This is now monochloropenthamine platinum 4 chloride. Or chloropenthamine platinum 4 chloride. I don't really see any need for this prefix mono. Now, when we get to this stuff, I expect that you're recognizing what's going on. We now got 4 ammonias in the first coordination sphere instead of 5 or 6. So in this stuff, since these platinum complexes are all octahedral, I must have 2 chloride ions coordinated. So immediately I'll write the formula. And when I write this Cl2, don't take this as a chlorine molecule. If you do that, that's minus 2,000. Not enough? Minus 5,000. Are we getting close? All right, second chloride ion. Where do you wish to put it? Well, green usually simulates chlorine. Chlorine, all right? So I'll take away one of these green ones. The rest are ammonias. I'll hold the model like this. Because when I hold a model like this, see this chloride ion? Here it is. Okay? Where's this one going to go? Well, it could go here, 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 or here. Tell me. Do I get structurally different complexes as a consequence of where the chloride ion goes? No, they're all octahedral. But do I get geometrically different complexes depending upon where chloride ion goes? The second chloride ion. Because if this chloride ion goes here, the bond angle is 90 degrees. If the chloride ion went here, 90 degrees. Here, 90 degrees. Here, 90 degrees. But if the chloride ion goes here, 180 degrees. So two possibilities now exist. We'll sketch them. This or this. N for ammonia. Here's where I had the first chloride ion. If the second chloride ion goes here, which is where I've shown it, or instead went here, or instead went here, or instead went here, they're all the same. Here's my two green chloride ions. Okay? If I have this picture, then I got a chloride ion up top and a chloride ion over there. Right? There's the picture. If the chloride ion is here and here, then I got this. Just thing floating around in space in solution. But if the chloride ion is like this, then the chloride ions are as far apart from each other as they can be. Whoop. What'd I do? Took away the wrong one. Giving us a different geometry for the first coordination sphere. What we have just looked at are stereoisomers, geometric isomers for the two possible tetramine dichlorocomplexes of platinum 4. And since these isomers are not the same, when the chloride ions are at a 90-degree angle with respect to each other versus a 180-degree angle, we got to distinguish between them with names. So I'm going to offer to you two names that are often used. Trans, cis. You've heard the word trans before. It means across or opposite from each other. 180-degree bond angle for the trans-oriented chloride ion. Cis, as close to each other as they can possibly be. That's what this means. 90-degree bond angle for the like chloride ion ligands. Now, what about this last stuff? The last stuff I got no moles of precipitatable chloride ion. That tells you every one of these chloride ions is coordinated. Because these coordinate bonds are strong. They're covalent bonds. All right? What's the charge on this complex? This last one. K plus PT NH3 Cl5. It's a -1 complex. please do not coordinate K plus. K plus is no valence electrons. It cannot be a ligand. All right? So now we got to this one. There's the skeleton for our pictorial representation of an octahedron, an octahedral complex. Where do you want to put in these chlorines? You want to put them in like this? Do you notice that if I put the chloride ions in the first coordination sphere in these geometric positions, the chloride ions are all cis with respect to each other, right? But what if the chloride ions were in the first coordination sphere in this geometric orientation? This set of chloride ions cis, this set of chloride ions cis, but this set of chloride ions trans. Cis and trans. So the cis-trans language leaves me at a loss. Notice, solid state. When the chloride ions are all as close to each other as possible, they're all occupying coordination positions which for an octahedron are on the same face. The same face, right? We'll draw a picture. Chloride, chloride, chloride. All on the same face. So we'll call it facial. But if the chloride ions are like this, notice that if the chloride ions like this, cis and trans, and I draw a circle around the exterior surface of the complex, all these chloride ions will lie in this circle. What's the name for a circle that goes around the Earth? Equator. Now there's also other geographical representation lines that go around the Earth. You heard about lines of longitude, latitude, stuff like that, right? Okay. Now, have you heard the word meridian? Meridian, an equator is a meridian of the Earth. Here, facial, they're all on the same face, or lying on this circle that goes around, a meridian. So when we got this, as an example, it becomes meridional. And now we can draw a distinction between these two possible platinum complexes for material number 5. The formula for the complex will remain the same. Trichloro, triamino, platinum 4 chloride. But which one do you have? Facial, which we can shorthand reference with FAC, or meridional, MER. More nomenclature. Now, the stuff regarding geometric isomerism, which we've now touched on, I'll pick up with on Friday because I need the models. So tomorrow in